All right, let's continue with continuity. Example 2. Determine whether the function is continuous at the given value. So we'll start with our first condition. Is it defined? So h of 2. Yes, it is. It's defined as 1. Now let's check the limit. So the limit, as x approaches 2, and note it's the same from left and right, so I'm only going to tackle this once. And then we get 2 squared minus 2 over 2 minus 2, which is undefined. Or is it? Okay, so remember, when we talk about the limit, if we get undefined, we should try to do something. Let's see if this factors. The limit as x approaches 2, x minus 2, x plus 1, over x minus 2, those cancel, is the limit as x approaches 2. And then we have here x plus 1. So this is 2 plus 1, or 3. So the limit does exist, and it is defined, but note they're not the same. So h of x is not continuous at x equals 2 because h of 2 does not equal the limit of h of x as x approaches 2. All right, let's look here at D. Okay, so first off, g of 3, remember our greatest integer function gives the greatest integer that's less than that, so 3 will come out 3. Now if we check the limit, we remember from before that if we do from left of 3, it will come out 2. And then if we do from the right of 3, our greatest integer function gives us 3. Therefore, the limit of our g of x, or greatest integer function, as x approaches 3, does not exist. So g of x is not continuous at x equals 3. All right. Now, when we talk about continuity, there are different types of discontinuities. The first of which is referred to as a removable discontinuity. This is when we can remove the discontinuity simply by filling in the hole or redefining what x is at a. In this case, we have a simple hole right here. We could simply define x equals 2 to be 3. In this case, we have 1, but we could simply redefine that to be at 3. So if we could simply remove it by changing one single point, it's called removable. These generally are indicated by holes in the function. Then we have what are called infinite discontinuities or non-removable discontinuities. This occurs at asymptotes. So we could define a single point, but there would be no way to fill this entire gap with that singular point. So we are not able to remove this discontinuity. Then we have jump discontinuities. These occur when the graph of the function jumps from one value to another without taking any value in between, and these are also non-removable. Okay, we're going to say this. A function is continuous from right at a if the limit from the right is what it's defined at. A function is continuous from the left at a if the limit of the function as x approaches a from the left is what it's defined at. All right, the question here, is the greatest integer function continuous from the right or from the left? Okay, so let's check. So the limit of our greatest integer function as x approaches a from the left. Now, we saw this in a homework last week. If we come at a number left of a, so visualize this on the number line. We're a here, over here we're the next integer, a plus 1, and over here we're the next integer, a minus 1. If we're to the left of a, say here, it's going to give a minus 1. Versus, if we do our limit from the right, as x approaches a, so say to the right of A, like here, it's going to give A, okay? Now we know mathematically speaking that f of A, if A is an integer, is going to give A, right? So we'd have that, right? So given A being an integer, we could see then that these two match, right? So we're going to note then that the limit of our greatest integer function as x approaches A from the right is equal to A. So our greatest integer function is continuous from the right. All right. A function is continuous on an interval, I, if it is continuous for every number in that interval. All of these are examples of cases where we are fully continuous on some interval, a to b. All right, show that this function f of x equals 1 minus the square root of 1 minus x squared is continuous on the interval negative 1 to 1. All right, so first off, this function here, is it defined for every number in this interval negative 1 to 1? Well, we see here that our function is defined everywhere except for when this piece is negative, right? So let's kind of note that. So we have here square root of 1 minus x squared, the part under the denominator specifically, it can't be negative because we can't square root negatives. So this must be greater than or equal to 0. So 1 must be greater than or equal to x squared, where x squared or x must be less than or equal to 1. Okay, so mathematically speaking, we must be between a 1 and a negative 1 because when we square root, we get plus or minus. So that seems fair. So we know that this function is fully defined from negative 1 to 1. Okay, so f of x has domain negative 1 to 1, so it is defined on negative 1 to 1. Okay, so we're good with that. First condition met. Okay, the next condition, does the limit exist? Well, let's check it. So the limit, as x approaches, let's say a, where a is in this interval, right? So we'll start with that actually. I think that might help us. Okay, so let a belong to the interval negative 1 to 1, and then let's consider the limit as we approach a of our function. So this becomes 1 minus the square root of 1 minus a squared. Now because a is in this interval negative 1 to 1, we know the square root here exists, so we know this exists. We also know that f of a is 1 minus the square root of 1 minus a squared. Note, these are equivalent, okay? So since the limit as x approaches a of f of x equals f of a, f of x is continuous on our negative 1 to 1. All right, theorem 4. If f and g are continuous at a and c is some constant, then the following functions are also continuous at a. The sum, the difference, multiplying by a constant, a product, and a quotient.